Load frequency control of a 4-area interconnected thermal hydronuclear wind power system with non-linearity using fuzzy logic PID controller. Abstract: this paper illustrates the load frequency control of a 4-area interconnected thermal hydronuclear wind power plant system using fuzzy PID controller. The settling time undershoot, an overshoot of the power system is observed with fuzzy PID controller. The thermal system is fused with boiler dynamics and generation rate constraints 13. The controlling approach assures that the frequencies and interchange of tie line powers are kept in given limitations 8. From the results it is clear that the peak overshoot and settling time for fuzzy PID controller is better than conventional controller and fuzzy controller when non-linearities is taken into consideration. It can also be observed that due to wind, which is a non-conventional power system, the settling time of the system increases as a whole. Time domain simulations are used to analyze the performance of the power system. The implementation of the 4-area system is done in MATLAB/SIMULINK package. Keywords: boiler dynamics, generation constraint, load frequency control, fuzzy PID controller and tie line power. Introduction. Load frequency control is done in an electric power system to maintain consistent frequency. During loaded conditions, the interconnected plants share power through tie line control. Tie line is used between power systems to allow bidirectional flow of power. Load frequency control becomes a necessity for power system because if the error in frequency exceeds more than 2%, the blades of the turbine are likely to get damaged. The frequency and tie line power will be fluctuated if any load variation happens, which will further reduce system performance and can damage load. Therefore it is mandatory to maintain frequency at stated limits. Most of the research conducted in this field neglect non-linearities, for example boiler dynamics and generation rate constraints in the thermal power plant for simplicity and better results 7-9. But if we go for practical solution, we need to incorporate these effects. In this paper we have taken non-linearity into consideration for our 4-area interconnected system. In literature, controllers based on fuzzy, conventional PID and neural networks 11 are proposed 9. There are various studies about different controlling mechanism having certain pros and cons. In most of the papers a LFC using a conventional PID controller is exercised and it is highlighted that the performance of this controller is better than others 12. However, if nonlinearity in a power system is taken into consideration, then conventional controllers fail to give an optimum result. Intelligent controllers can be replaced with PID controllers for quick and better dynamic responses. Fuzzy logic controller is usually more useful than conventional controllers because it is faster and more productive in nonlinear applications. Fuzzy logic controller is used to reduce variations on system outputs. In this paper, LFC of thermal hydronuclear wind power system is implemented using fuzzy PID controller. 2. 4-area power system. Power systems mostly comprise of multiple areas which may consist of nonlinear behavior 4. These areas are interconnected to each other by tie line which need controlling of power flow and frequency 5. Fig 1 demonstrates a 4-area interconnected power system used in our research. Fig 1 4-area interconnected power system. Area 1 encompasses a thermal power plant consisting of a speed governor, steam turbine, electric generator, and a single-stage reheater. In order to develop a realistic model, all nonlinearities related to the system is incorporated. Nonlinear mostly relates to how valve position are uninterrupted with respect to change in speed 1. Boiler dynamics on the other hand relates to how reheater can actively receive steam from boiler. 3. Mathematical modeling of 4-area power system. 1. Where A is system matrix, B is input matrix, F is disturbance matrix, X is state vector given in equation 2, U is control vector given in equation 3, is disturbance vector given in equation 4, 3. For nonlinearity. A. Boiler dynamics. In this paper a drum-type boiler is incorporated. Pressure control, boiler storage, and fuel system transfer functions are considered in the boiler leading or turbine modes of operation. The Fig 2 shows the simulated model of boiler 13. B. Generation rate constraint. In practical system, due to mechanical and thermal restriction, the rate at which output power can be adjusted has a limit specified to it too. This limit is termed as generation rate constraint. Fig 3 shows the simulated model of generation rate constraint 13. V. Complete SIMULINK model of 4-area power system. 6 controllers. A. PID controller. A PID controller continuously evaluates an error value as the difference between a desired signal and a measured process variable, and resultant error is multiplied with the proportional constant. Integral mode is used to remove the steady state error which could not be removed by proportional mode. 10 is the integral constant. Derivative mode in the controller improves stability of the system and increases gain and decreases time constant, thereby increasing speed of the controller response, is the derivative constant. B. Fuzzy controller. If we further want to improve the transient response and settling time, we go for intelligent techniques such as fuzzy logic. This controller works on the basis of sets. These sets are represented by membership function 16 and output is based on degree of membership function. Therefore, the fuzzy logic controller is used to get optimal result. See fuzzy-PID controller. It the combination of fuzzy logic and conventional PID controller, which gives better transient response and setting time. Fig 4, Fig 5, Fig 6 shows the input-output membership functions for this controller. Table 1 shows the rule table 11 of fuzzy logic where inputs are ACE and .ACE. 7. Simulation and results. Simulations were performed with the parameters given in the appendix, with conventional PID controller, FLC and fuzzy-PID controller for the 4-area system. Simulation was carried out for step load change of 10% given simultaneously for each area. The GRC for thermal system is considered for 1%. The change in frequency of the system with PID, fuzzy and fuzzy-PID is given in Fig 7, the settling time, undershoot and overshoot are observed and tabulated in Table 2. Fig 8 shows the frequency response of 3-area, thermal hydronuclear, which are conventional systems with fuzzy-PID controller. Fig 9 shows the frequency response of 4-area with wind incorporated, which is a non-conventional system. Table 3 shows the comparison table of conventional system with a non-conventional system. It is observed that for a 4-area system as compared to fuzzy and PID, fuzzy-PID controller gives better response based on time domain parameters and maintains the system frequency. Also, the result shows that by introducing wind system the settling time increases but maintains the system frequency and is in constant steady state value. 8. Conclusion. In this paper, load frequency control of 4-area interconnected thermal hydronuclear wind power plant system is performed using fuzzy-PID controller. From results we can analyze the settling time, overshoot and undershoot of fuzzy-PID is better as compared to PID and fuzzy controllers. Fuzzy-PID controller gives the best response when uncertainty and non-linearity are considered.